In this video, we'll explore how to build a large-scale video search system using YouTube as our motivating example. The core problem is simple to state. Given a user's text query, return the most relevant videos. But solving it at scale, with billions of videos, multimodal content, and diverse user intents, requires careful system design. Let's dive into the design of YouTube video search. The following provides an overview of the key contents. We'll walk through this challenge step by step, covering requirement clarification, how to frame the task as an ML problem, data preparation, model development, evaluation, and serving infrastructure. The problem is to find the most relevant videos for a given input text, and the results should be ranked based on the video's relevance to the query. Here are some good questions to ask in the requirement clarification phase. Is the input query text only? Is any training data available? Do these videos have titles, descriptions, and tags? Do we need to support other languages? How many videos are there? In YouTube video search, we're essentially trying to retrieve the most relevant videos given a user's query. Depending on the query type and the data modality, we can approach this problem from two complementary angles: visual search and text search. Text search, inverted index. For more traditional keyword-based queries, e.g., how to play guitar, NASA launch, we rely on text search using an inverted index. This is a classic information retrieval technique. Each word in the corpus maps to a list of videos or documents containing that word. At query time, we quickly fetch candidate videos by matching terms from the user query to this index. It's extremely efficient, scalable, and forms the first-pass retrieval system before more sophisticated re-ranking kicks in. Inverted indices are especially effective when metadata is rich and well-labeled, like titles, descriptions, or captions. Visual search. Representation learning. For cases where we want to retrieve videos based on visual similarity, such as using a thumbnail image or visual content from another video, we treat this as a representation learning problem. We train deep neural networks, typically CNNs or transformers, to convert videos into compact embeddings that capture their semantic visual content. The goal is to learn an embedding space where similar videos are close together and dissimilar ones are far apart. During search, we embed the query, e.g. a video or an image, and retrieve videos whose embeddings are nearest neighbors in that space. This is crucial for handling queries based on video content, style, or structure, not just text metadata. In summary, we frame YouTube video search using two core approaches. Visual search via deep representation, learning to handle queries grounded in video content. Text search using inverted indices for efficient keyword-based retrieval. These two approaches can be used independently or combined in a multimodal system to improve overall relevance and coverage. In a system like YouTube video search, preparing high-quality data is critical because we're dealing with multimodal inputs, both text and video. The better our pre-processing, the better our model can learn and generalize. Preparing text data. Text normalization. We begin by cleaning the text in titles, descriptions, captions, and tags. This includes lowercasing, removing punctuation, handling special characters, and sometimes expanding contractions, like don't to do not. Tokenization. We split the normalized text into individual tokens. These could be words, subwords, or even characters, depending on the tokenizer. This step breaks down the input into meaningful chunks for processing. Tokens to IDs. Each token is then mapped to a unique ID using a vocabulary. These token IDs serve as input to text models like transformers. We may also include special tokens like CLS, SP, or PAD, depending on the model architecture. Clean and well-structured text data is essential for accurate language understanding and retrieval. Preparing video data. Decoding. Raw video files are first decoded into frames. We extract RGB pixel data from compressed formats like MP4 or WEBM. Sampling. We don't process all frames due to computation limits. Instead, we apply frame sampling. Uniform sampling. Extract one frame every n seconds. Scene-based sampling. Detect shot boundaries and sample representative frames. Resizing. Extracted frames are resized to a standard resolution, e.g., 224 by 224, to match the input size of CNNs or video transformers. Scaling, normalizing, and correcting. We scale pixel values to a specific range, e.g., 0, 1, or -1, 1. We also normalize using dataset-level mean and standard deviation, just like in image models. Optional: color correction, deblurring, or lighting adjustments if needed to improve visual quality. Preparing video data is computationally intensive but crucial for extracting meaningful visual representations. In short, our data preparation pipeline ensures that both text and video inputs are clean, consistent, and compatible with downstream neural models. This step lays the foundation for effective multimodal learning in YouTube search. In model development, we will explore different encoders for text and video and also focus on model training. Text encoder, from bag of words to deep contextual embeddings. YouTube metadata, titles, descriptions, tags, subtitles contain rich semantic signals. The challenge is to encode them into vector representations that meaningfully capture linguistic and contextual nuance. Bag of words, BAW. Simplest representation, a high-dimensional sparse vector with word counts. Lacks word order and context, but useful as a baseline for text retrieval. TF-IDF, term frequency inverse document frequency. Weights rare terms higher than frequent ones. Enhances discriminative power over BAW by reducing noise from common stop words, e.g., video, watch, you. Embedding layer, lookup table. Learns a dense vector for each word during training, e.g., 300D. Words with similar meanings are closer in embedding space. Typically initialized randomly or with pre-trained vectors like glove or fast text. Word2Vec. Learns word vectors by predicting context. CPOW. Averages context to predict target word. Skipgram. Predicts context given the target word. Captures syntactic and semantic regularities. Enables vector arithmetic like king, man plus woman is almost equal to queen. Transformer-based encoders, e.g., BERT, Roberta, GPT-3. Utilize self-attention to model contextual dependencies across tokens. BERT, bidirectional encoder, captures full context, fine-tuned for ranking or classification tasks. GPT family models are generative and suitable for tasks like query reformulation or summarization. Fine-tuning on domain-specific data, e.g., YouTube metadata corpus, significantly boosts performance. For retrieval, dual encoders based on BERT are common, one for query text, another for document text. Embeddings are compared using cosine similarity. Video encoder, temporal and spatial semantics. Processing videos requires modeling both the spatial layout, objects, scenes, and temporal dynamics, motion, transitions. Video-level models. 3D CNNs, e.g., C3D, I3D. Extend 2D convolution over time dimension. Effective for short clips with consistent motion, e.g., sports, action. Timesformer/video swing transformer. Use spatiotemporal attention across frame sequences. Outperform CNNs on large-scale benchmarks like kinetics. Frame-level models. Process frames independently with CNNs, e.g., ResNet, EfficientNet, or VIT, vision transformers. Embed sampled frames, then aggregate via average pooling, RNNs, or attention. More scalable for long videos where full frame processing is impractical. Easier to cache and reuse frame embeddings across different models. For massive video corpora, frame-level embedding with late fusion is more efficient and often sufficient for retrieval. Contrastive learning, multimodal embedding alignment. The goal is to align text and video representations in a shared latent space such that relevant pairs are close and irrelevant ones are distant. Training objective, contrastive loss, often implemented as InfoNCE or cross-entropy over softmax similarity scores. Positive pairs, ground truth video-text pairs from metadata or captions. Negative pairs, in-batch negatives, other video-text pairs in the same batch. Hard negatives, videos with semantically similar metadata but different content, mined to improve model robustness. Implementation details. Similarity function, product or cosine similarity between normalized embeddings. Temperature scaling, applied before softmax to control sharpness of the similarity distribution. Multimodal transformers, e.g., clip, Florence, can jointly encode video and text with cross-attention, though dual-tower encoders scale better for retrieval. Contrastive learning is foundational for large-scale search systems, as it enables efficient nearest neighbor retrieval through pre-computed embeddings. Model development for YouTube video search must balance semantic fidelity and computational efficiency. Deep transformer-based encoders capture richer semantics, but require careful optimization. Meanwhile, training with contrastive loss ensures that cross-modal alignment directly optimizes for retrieval tasks. The system's ability to generalize to unseen queries hinges on the diversity and quality of training data and the robustness of these encoders. Evaluating the effectiveness of a video search system involves measuring how well it ranks relevant videos in response to user queries. This phase includes offline metrics for technical performance and online metrics that reflect real-world user interactions. Offline metrics. Offline evaluation uses a static labeled dataset to assess model performance without real-time user data. It helps ensure that the model is functioning as expected before being deployed. Precision at K. Precision at a given rank K measures how many of the top K results are relevant. For example, if you rank the top 10 results for a search and 7 of them are relevant, the precision at 10 is 0.7. This metric helps to understand the accuracy of the top-ranked results and is vital when precision at the top is a priority. Mean average precision, MEP. Averages precision scores at different recall levels for each query. This metric is particularly useful when evaluating how well a model performs over multiple queries, providing a holistic view of its retrieval ability. Recall at K. Recall at a given K measures how many relevant results are retrieved in the top K positions. A higher recall at K means more relevant content is being retrieved in the top results. It is critical for ensuring that the search system doesn't miss important videos. Mean reciprocal rank, MRR. MRR calculates the rank at which the first relevant result is found. For example, if the first relevant video appears at rank 1, the MRR score is 1.0. If it's at rank 3, the score is 1/3. This is a good metric for tasks where users expect the top-ranked video to be relevant immediately. Online metrics. Online evaluation is conducted with live user data, providing insights into how well the search system performs in production. Click-through rate, CTR. CTR measures the percentage of times a user clicks on a video from the search results. A higher CTR suggests that the search results are enticing and relevant to the users. However, it's important to keep in mind that CTR can be influenced by factors like thumbnails and titles, so it should be interpreted carefully. Video completion rate. This metric shows how often users finish watching a video after clicking on it. If a video has a high completion rate, it indicates that the video matches the user's intent and holds their attention throughout. Low completion rates can suggest poor relevance or content mismatch. Total watch time of search results. This metric captures how much total time users spend watching videos from the search results. It provides insight into how engaging the search results are and is particularly useful for evaluating longer-form content, where engagement might span multiple videos or sessions. By combining offline metrics like precision at K, MAP, and MRR with online metrics like CTR, video completion rate, and total watch time, we can get a complete picture of how well the video search system performs. Offline metrics allow for quick and repeatable evaluations during development, while online metrics ensure that improvements translate into better user experiences in production. Once the model is trained and ready for deployment, it's crucial to ensure that predictions are made quickly, accurately, and efficiently. Serving pipelines are designed to handle the prediction requests, process them through various stages, and deliver the final results to users. For YouTube video search, this involves visual search and text search, and then merging the outputs in an intelligent way. Prediction pipeline. Visual search. Nearest neighbor. When the user submits a query with an image, for example, a thumbnail or a specific video frame, the nearest neighbor search retrieves similar videos based on their visual embeddings. This is typically achieved using an efficient nearest neighbor search algorithm, such as approximate nearest neighbor, ANN, or KD trees, to find the closest matching visual representations in the index. The goal is to return visually similar videos based on content. Text search, Elasticsearch. When the user queries via text, such as a video title or description, Elasticsearch is used to efficiently search through the indexed text data. Elasticsearch is a powerful tool for textual search and ranking, and it is optimized for speed, scalability, and full text indexing. It allows us to match the user's text query to the most relevant videos based on keywords, phrases, and metadata. Fusing layer, combining outputs from both searches. Once we have results from both the visual search and text search, the fusing layer combines these two outputs to create a unified ranking list. This step ensures that both the semantic relevance from text and visual similarity from images are considered, offering a more comprehensive and accurate list of video results. The fusion could be as simple as weighted averaging of rankings or could involve a more complex model to intelligently merge these results. Re-ranking service, incorporating business logic. After fusing the search results, we apply business logic in the re-ranking service to further refine the final order. This can include factors such as user personalization, trending content, geolocation, or recency. The re-ranking ensures that the videos shown are not only relevant based on the query, but also aligned with business goals like boosting engagement or highlighting sponsored content. Text indexing pipeline. Text indexing involves building and maintaining the index of all textual data related to videos, such as titles, descriptions, tags, and metadata. The pipeline should ensure that new video data is indexed regularly and that the indexing system is optimized for fast retrieval. Video indexing pipeline. Video indexing involves creating and storing embeddings for video content, such as the visual features extracted from the video frames and audio embeddings if needed. The pipeline handles both initial indexing of newly uploaded videos and updating the index as videos change or get updated. It ensures that the visual search system has access to up-to-date and accurate video representations for fast and efficient searching. By combining the visual search pipeline, which leverages nearest neighbor techniques, with a text search pipeline using Elasticsearch, and adding a fusing layer and re-ranking service, we can build an effective and scalable YouTube video search system. This approach ensures we not only provide accurate results, but also optimize for user engagement and business goals.